Welcome back everyone. In this video, we are going to talk about how to solve a Bernoulli's differential equation. Okay, Bernoulli's differential equation. A differential equation of this form, dy dx plus p of x times y equal to q of x times y to the power of n, is called a Bernoulli's differential equation. Remember, the linear differential equation is similar to this. For linear, we have dy dx plus p of x times y equal to q of x. Okay, but for a Bernoulli's differential equation, this is what we have. You can actually watch my video on linear differential equation. So let us solve a problem under Bernoulli's differential equation. The first question. Solve the equation dy dx plus y equal to y squared. This is the question, and we are going to solve it. So this question or this equation is already in the Bernoulli's differential equation form, like I wrote earlier. Dy dx plus p of x times y equal to q of x times y to the power of n. You can compare it. P of x here is 1. Okay, that is it. Then q of x here is also 1. Y to the power of 2 here is the y to the power of n that we have here. So it's already in Bernoulli's differential equation form. So if we are giving a Bernoulli's differential equation and the equation is not in this form, the first thing is to convert or change the equation into this form. What we are going to do now is this. We are going to reduce this differential equation, this Bernoulli's equation, into a linear differential equation of the first order. Of course, this is the first order differential equation. Okay, so this is how to do it. The first thing is to divide both sides by this y raised to the power 2. Divide both sides by y squared. So if we divide both sides by y squared, we are going to have 1 over y squared dy dx, okay, plus this is y over y squared equal to y squared over y squared, which is actually 1. So what will this give us? 1 over y squared is y to the power of minus 2 dy dx plus y over y squared is actually 1 over y. This is y times y. So y will cancel one of these. Y at the bottom, we're having 1 over y. And 1 over y itself is y raised to the power minus 1. And here we have 1. Okay. So the next thing is this. We are going to introduce a new dependent variable, z. Let z be equal to this, y to the power of minus 1. So we will take the derivative of z with respect to x. Okay, so this is it now. The z dx is equal to, if we are differentiating this with respect to x, this is how it will be. Let's differentiate this. Minus 1 times 1, that's minus 1, times the y to the power of minus 1 minus 1. The derivative is with respect to x. Dy dx. The z dx equal to minus y to the power of minus 2 dy dx. So remember I said that we are changing this Bernoulli's equation into a linear differential equation. See what I have here. Y to the power of minus 2 dy dx. I can see it here, but I'll have to take away this minus. Okay, so let me remove this minus. If I remove this minus from here, okay, here will be plus and here will be minus. That is if I divide both sides by what? Minus. Okay, so I'll be having minus the z dx equal to y to the power of minus 2 dy dx. So everything here is what I can see here. That means in place of this now, I can write minus the z dx. That's what it means. We're going to plug this into this. Minus dz dx, okay, plus, this is y to the power of minus 1. Remember we said let z be equal to y to the power of minus 1. So in place of y to the power of minus 1, I'm going to write z. And this is equal to what? 1. The z dx will have minus z equal to what? Minus 1. We have reduced this Bernoulli equation to this. So we will now apply the procedures for solving a linear differential equation to solve this linear differential equation. And at the end, we are going to substitute the value of z here, which is y to the power of minus 1, in the solution. For linear differential equation, it is of the form dy dx plus p of x into y equal to q of x. So in this case, I can say the z dx, since we are dealing with the z as the dependent variable, plus p of x into y equal to q of x. This is the form that we have here. P of x is minus 1, q of x is minus 1 as well. Okay, so let us solve this differential equation now. Remember to hit on the subscribe button. Okay, turn on notifications as well to get updated whenever videos come up in the future. So let's go ahead. Now, this is the equation we are solving. So for linear differential equation, after the equation has been reduced to the standard form that we have now, the next thing is to determine the integrating factor. I want to keep this. Okay, let's determine the integrating factor. And the integrating factor is e to the power of the integral of p of x dx. This is the integrating factor. So let us go now. We said that p is what? Minus 1. So we have e to the power of the integral of minus 1 dx. Alright? So the integral of minus 1 dx is minus x. So this is the integrating factor. Having gotten the integrating factor, the next thing to do is to plug in these integrating factors into that equation I gave to you in the previous video for linear differential equation. I'm going to write it again. This is the equation. I wrote, let me erase this part. The equation is this. Y times integrating factor is equal to the integral of the integrating factor times q of x dx. This is the equation. So we are dealing with z now, not y. So the formula we are going to plug this integrating factor into is this. Z times the integrating factor is equal to the integral of the integrating factor times q of x dx. Alright, so let's go ahead. So we have z times, this is the integrating factor, e to the power of minus x. We have e to the power of minus x times q of x is minus 1. Compare it. Minus 1 dx. So z e to the power of minus x is equal to, this is actually minus the integral of e to the power of minus x dx. So z e to the power of minus x is equal to this. Minus, what is the integral with respect to x of e to the power of minus x? It's simple. Write the e to the power of minus x and divide by the derivative of minus x with respect to x. Differentiate minus x with respect to x, you're going to obtain minus 1. Alright? So minus will take away minus. We then have this. Z, okay, e to the power of minus x equal to e to the power of minus x plus c. Dividing both sides by e to the power of minus x. E to the power of minus x So this will cancel out. Z is now equal to 1 plus c over e to the power of minus x. This is the solution to that differential equation. I just erased it. So let me write it again. The equation was dz dx minus z equal to minus 1. Good. This is the linear equation that we solved to get this. Okay. But remember earlier that we said this is the given differential equation that we have to solve. We made a substitution. Let z equal to y raised to the power minus 1. You can recall, we said let z be equal to y to the power minus 1. So what we are going to do now is this. We are going to make back this substitution, z equal to y to the power minus 1. So in place of z now, we are going to write y to the power minus 1. So that we can obtain the general solution to the Bernoulli's equation. Remember, we reduce this Bernoulli's equation to this linear equation. And this is the solution to this linear equation. To get a solution to the Bernoulli's equation, this substitution will be made back again. Z is now y to the power of minus 1. Y to the power of minus 1 equal to 1 plus. I can actually write this as c e to the power of x. If I take the inverse of 1 over e to the power of minus x, the minus here will go away. So this is what we have. So this is 1 over y equal to 1 plus c e to the power of x. This is over 1. So if I reciprocate both sides, y over 1, which is y, is equal to 1 all over 1 plus c e to the power of x. This is the general solution of this Bernoulli's equation. So this is what we are looking for actually. Let us take one more example. Let's solve this problem that says solve dy dx plus 18y dy dx plus 18y equals to y to the power of minus 5 times e to the power of 2x. Okay, this is also another Bernoulli's equation that we are going to solve. Let us see how to get the general solution. The Bernoulli's equation is of the form. Let me put it here. Dy dx plus p of x into y equal to q of x times y to the power of n. Alright. So we can see something like this there. P of x is 18. Q of x is e to the power of 2x. And y to the power of n is y to the power of minus 5. Alright. So all we have to do is to first of all divide both sides by y to the power of minus 5. Divide both sides by y to the power of minus 5. And so if you do that, you are going to obtain y to the 5th dy dx. Hello. Take note. If I have 1 over y to the power of minus 5, the inverse is actually y to the power of minus 5, which is y to the power of 5. That's how this is gotten. So if I divide this by this, I'm going to obtain 1 over this, which is equivalent to this, plus 18 times, this is y to the power of 1, divided by what? Y to the power of minus 5. So in this it says we have 1 y to the power of 1 minus 5. This is actually a plus. And what is this equal to? 6. So this is y to the power of 6 equal to e to the power of 2x. Divide this by y to the power of minus 5. This one will cancel the one at the bottom. So what we have to do now is this. Let z equal to y to the power of 6. Okay. We are not concerned about this 18, which is p of x, just the y. So the derivative of z with respect to x is equal to this. 6 times 1 is 6. 6 minus 1 is 5 dy dx. right? This is it. So we are going to convert this Bernoulli's equation into a linear first order differential equation. Of course, this equation is of the first order. So if I look at this very well, this first term here, I have y to the power of 5 dy dx. And if I look at this now, I can see 6y to the power of 5 dy dx. Two things can be done. It's either I remove this 6 from here, so that I'll be having y to the power of 5 dy dx, which is equivalent to this, or I will leave the 6 here and multiply through by 6, so that this one will now contain 6 as well. So what I want to do is, I want to multiply through by 6, because if I divide both sides by 6, later I will still multiply through by 6 to remove that 6 from the bottom. So let me just multiply through by 6 once and for all. Okay, let's say this is equation 1. So if we multiply this equation 1 by 6, we'll be having 6y to the 5th dy dx plus 6 times 18 is 108. 108y to the power of 6. And this is 6e to the power of 2x. This is equation 2. Okay, so what we have here now is exactly what is here. So we can now say, in place of this, we are writing the z dx. That is the point. So we have now, this is now the z dx plus 108. Y to the power of 6 is what? Z. Z equal to 6e to the power of 2x. So this is now a linear first order differential equation. Remember the form of a linear first order differential equation. The y dx plus p of x into y equal to q of x. In this case now, y is z. Okay, so the z dx plus p of x times z equal to q of x. That's the form we have here. So let's solve this linear differential equation. Let's obtain a general solution. The first thing to do is to determine the integrating factor, which is e to the power of the integral of p of x dx. And that is what? E to the power of p of x is 108. The integral of 108 dx. And what would that be? E to the power of 108x. Okay, this is the integrating factor. So we'll now plug this integrating factor into that our popular formula. I'm saying popular because we have been using it over and over again. That formula is, in terms of z and x now, z times the integrating factor equal to the integral of the integrating factor times q of x dx. So z, the integrating factor is this, e to the power of 108x, e to the power of 108x. What's q of x? Everything here. That's 6e to the power of 2x. 6e to the power of 2x dx. So this is z e to the power of 108x equal to 6 can come out. This is e to the power of 108x e to the power of 2x. If I add them up, that's the powers, I'll have 110x. By the law of indices, they have the same base, so the powers can be added. So z e to the power of 108x is equal to 6 times. What is the integral of this with respect to x? We have e to the power of 110x divided by 110. Okay. Remember, for the integral of e to the power of kx dx, it is e to the power of kx all over what? K plus c. So this is it now. 2 here is 3, 2 here is 55. Okay, don't forget we said that let z be equal to y to the power of 6. Okay, let me keep it here. Z equal to y to the 6th. We are going to make use of it. So we have z e to the power of 108x equal to 3 upon 55 e to the power of 110x plus c. All right. We can divide both sides by e to the power of 108x. Z is now equal to 3 over 55. This is e to the power of 110x. This and this have the same base, so I'll subtract their powers. Minus 108x. And this is plus c. If I'm dividing this by this, it will be c all over e to the power of 108x. So just like I did earlier, I want to write it as c times e to the power of minus 108x. So if I take the inverse, it means that the power becomes negative. So z is equal to 3 upon 55 e to the power of, this is actually 110 minus 108 is 2. So this is 2x. Alright, we are done. But remember that z is equal to what? Y to the power of 6, like we said earlier. So this now becomes y to the power of 6 equal to 3 over 55 e to the power of 2x plus c e to the power of minus 108x. So we can choose to remove this 6 from here by taking the 6th root of both sides. 6th root is equivalent to the power of 1 over 6. Y will now be equal to 3 over 55 e to the power of 2x plus c e to the power of minus 108x, all to the power of what? 1 upon 6. So this is actually the general solution of this differential equation. This is the equation that we are solving. So this is how it is done. This is how to solve Bernoulli's differential equation. I hope you enjoyed the video. Remember to subscribe and turn on notifications. Like and share the video to your friends and to your course mates. I am the complex analyzer.